Welcome to cryptography session. Today I am going to give an introduction about Unit-3. Unit-3 is a public key cryptography. The topics which are all covered under Unit-3 are mathematical concepts of asymmetric key cryptography and public key cryptography algorithms. So if you consider mathematics of asymmetric key cryptography, there are 6 different notations are available. Those are Euler's Totient function, Fermat's theorem, Euler's theorem, Chinese remainder theorem, factorization, exponentiation and discrete logarithms, testing for primality. So these concepts are the backbone for construction of a public key cryptography algorithm. So if we consider a public key crypto system, it contains two types of keys are available. So each end user contains two keys. Those key names are private key and public key. Public key may be open to all, but private key should be secret and it should kept secret with themselves. So that is the concept behind public key cryptography. So if you want to go for a key representation, there is a need of checking notations. That means whether the number should be taken as a prime number or not. For that concepts, these 6 mathematical notations are available. Using these notations only, the algorithms are described. So there are 3 types of algorithms are available. One is RSA algorithm, Elgamal crypto system, and elliptic curve cryptography. So these are all 3 different public key cryptography algorithms. For generating a key management technique is available that is called as Diffie-Hellman key exchange algorithm. So these are all the overview idea of Unit-3. Let us take each one. So the first mathematical notation is Euler's pi function. It is also called as Euler's Totient function. So it is represented as pi of n and it contains few rules in it. If you want to calculate pi of 1, the answer is 0. Pi of p is equal to p minus 1 where p should be a prime number. Suppose if the number is a composite number, that should it contains the factors in it. So pi of m cross n is equal to pi of m into pi of n. In this situation, m and n are relatively prime. So if m and n are relatively prime, the GCD of m comma n should be 1. So this is the third rule. And fourth rule, if we able to write a number in prime power factor, so it is described as pi of p power e. So the value of pi of p power e is equal to p power e minus p power e minus 1. So these are all the 4 basic rules. Let us take an example for each one. What is the value of pi of 13? Here we take 13 is a prime number. So we should apply rule number 2. So the rule number 2 is pi of p is equal to p minus 1 where p is a prime number. So using that concept, pi of 13 will be written as 13 minus 1. So the answer is 12. Then what is the value of pi of 10? So 10 is a composite number. So we should apply rule 3. With the rule 3, pi of m into n can be written as pi of m into pi of n, and m and n are relatively prime. So that is the concept. So 10 can be written as pi of 2 cross pi. So which is rewritten as pi of 2 into pi of 5. So pi of 2. So 2 is a prime number. So p is a prime number means we should apply rule 2. So answer for pi of 2 is 1. 5 is a prime number. So pi of 5 is equal to 5 minus 1. So answer is 4. 1 into 4, 4. So the answer for pi of 10 is 4. Let us take another example. Pi of 240. 240 can be written as 16 into 3 into 5. So 16 can be rewritten as 2 power 4. So for this concept, for writing, so these are all 3 factors, m, n and p, like that. So this is pi of 2 power 4. It should be, so 240 can be written as pi of 2 power 4 into pi of 3 into pi of 5. So you apply rule 4 for these concepts. So pi of p power e can be written as p power e minus p to the power e minus 1, where p is a prime number. So here 2 is a prime number, so this 2 power 4 can be rewritten as 2 power 4 minus 2 power 3. Answer for pi of 3 is 2. Answer for pi of 5 is 4. So 2 power 4 minus 2 power 3, 16 minus 8. So the answers are 8 into 2 into 4. So 8 into 8, 64. So this is the answer for pi of 240. Let us take the fourth example, pi of 49. Sometimes we wrongly written as pi of 7 into 7. And we write the answer for 7 is a prime number, so pi of 7 is 6. This is also a prime number, so 6 into 6, 36 we write it. But if you write like this, m and n should be relatively prime. Here m and n are same number, so we cannot able to write these answer. So instead of this, we should rewritten as 7 squared. And if you write 7 squared, we should apply rule number 4. So from the rule number 4, pi of 49 is equal to pi of 7 squared. So that is equal to 7 squared minus 7 power 1. So 49 minus 7 is 42. So the correct answer for pi of 49 is 42 and not 36. So in this way, we can able to do Euler's Totient function. So this is another example, pi of 14. So 14 is a composite value. Pi of 7 into pi of 2. 2 and 7 are relatively prime. So answer for pi of 7 is 6. Pi of 2 is 1. So 1 into 6, 6. So this pi value is also calculated. So this pi of n is also calculated the number of elements of a given group. So this is also like that. So if you take Z14 star, it written as a group. For the given group, we can able to write the number of elements in it. So for calculating the number of elements, we may able to apply this pi of n concept. So according to pi of n, so the answer is 6. So totally 6 elements are only available in Z14. So if you take Z14, the numbers may be from 0 to 13. But those numbers should be relatively prime to 14 number. So what are the number relatively prime to 14 means 1, 3, 5, 9, 11 and 13 only. These numbers are relatively prime to Z14. So the count of or the number of elements are 6. So the answer is also 6. So this Euler's Totient function is also able to calculate the number of elements of a given group. The Fermat's theorem and Euler's theorem concepts will be discussed in next session. Thank you.